So the start of postulate number 1. So, hello?
Nice. Solid.
It just worked. I just use the
Yeah, it's
arrow.
fine.
Okay, so the postulate itself says that the state of a quantum mechanical system is completely specified by the wave function psi of RT, where R is position and T is time. Actually, I'll go back. So I have highlighted a couple of different words here because I think that these are the most important things to define in order to understand the statement itself. So I'll start with quantum mechanical system, which is a system where the behavior of the particles can be explained mathematically using 4 main principles. So that would be the quantization of energy, which is Planck's principle that energy is transferred in discrete packets and is not continuous. And then the second one is the wave-particle duality, where systems can behave like waves and like particles. The next one is the uncertainty principle, which states that the position and momentum of particles can't be determined at the same time. So you can only do one or the other. And then the fourth one is the correspondence principle, which says that the behavior of any system is the same on the quantum level and on macro level. So that's basically what a quantum mechanical system is. So then the next thing is the quantum state itself, which is it's basically some mathematical statement that has all of the information about a system, which is used for finding probability distributions for observable properties. It's a probability distribution because of the uncertainty principle. So you can't find the exact value, you can just find the probability of it. Do we want, okay. Live transcript on. Okay. So quantum states can be pure or they can be mixed. A pure quantum state is it's just the most basic form. You know, it's described as array in Hilbert space over complex numbers, which I will admit I don't exactly understand, but as far as I understand it, it's combining our like observable knowledge with abstract imaginary space. So a mixed quantum state can be described by density matrices, which are operators that act on Hilbert spaces. Mixed quantum states can be the sum of pure quantum states. Yeah, that's the statement. Okay. I forgot what else I was going to say, so I'll just move on to the next slide. So the most important thing of this postulate is the wave function. So the wave function describes the probability of finding particles or fields in a certain position at a certain time. So wave functions are pure quantum states because they are represented by that vector in Hilbert space. And they can be manipulated to find other observable properties. So you can use the basic wave function formula to find other properties. So the conclusion is that if the wave function itself is a pure quantum state, then psi of RT can describe the state of a quantum mechanical system, which is the statement of the postulate.
Okay. Thank you for being great and important, and thank you for presentation. So, paper is open to discussion.
Yes.
Melody.
Melody, well done.
No, it's not open hands. It is upload.
Yeah, it's 5 minutes.
Okay. So anyone online
Oh,
Once to ask which nice.
I think someone needs to mute.
I think.
Okay, question number one, what was it again? How to get probability out of wave function. So I have here my little cheat sheet, which has the math on it. So, I mean, it would be backwards, I think. Okay, so I don't really know. But for okay, hold on. So, okay. Do I need markers? This is science. Okay, so from what I have learned in my research, there's the Drock notation, which is the bra-ket notation, where you have the ket, which is it's mathematically a vector, and then physically it is the state of the quantum system. And then so that's ket. Then you have the bra, which is mathematically, it maps each vector to a complex plane. So we have that. So when you combine them together, you have the linear functional x on the vector, which is, it's kind of confusing, but that's how I understand it. So when you have pure quantum states, it's just this, I think.
Okay. Thank you for trying. and as long as you speak, as less time is for other classmates, so they should appreciate it very much. Anyone wants to be a little more specific, like probability? I want to probability. So Melody told that as far as we know wave function, we can get probability or probability density. Which mathematical operation you need to do with wave function to get probability or probability density?
You take the integral.
Okay, integral of what?
Integral of the square modulus.
Okay, yes.
Yeah, hold on.
So, okay, this is, so the square modulus just means absolute value. So the square modulus is
this related? Is this with her postulate, or is this something that we all?
okay. So this is the square modulus.
So this one is probability density.
Yeah.
What she told,
Yeah,
in a
this
space
is
and time.
probability density. So that equals rho.
And then it is we can go
Okay.
in more details later.
Yeah. So if
This
you,
exactly answers my question.
oh, okay.
I really would like to speak for another hour. We need to give speech to others.
Sorry, I'm talking too long.
It's appreciated. Any more questions? One question, two questions. So let's thank for one again.
Yes.
So now we do have the next speaker. And he will teach us postulate number 2.
Don't even know.
Maybe he will,
Oh,
I'm going
maybe
to.
he will complement teaching about postulate number 2 also with a brief mentioning of the concept of operator commutation.
Yeah, well, this is gonna be something. That's the- That's the
the
best way to put it. Maybe, hopefully. Okay, I just want to make a note though that the like transcription of Zoom is actually really good. It's like better than anything I've ever seen.
Yeah, why?
Where do we?
Yeah.
go?
20 more minutes.
Do, 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 do.
It is in
It's already pulled up on the.
Oh, is it?
Yes.
Oh, heard. Here we go. I wasn't exactly planning on this being a super. I'm not trying to. Is this the okay? So we're doing postulate 2. Yeah, my name is Sam Stevens. I did. Sorry, I was trying to figure out where things were. Okay, so an important note before we get going is that I know in physical chemistry we refer to the operator as a Hamiltonian, but that it's technically considered a Hermitian. I believe I'm saying that right. And that a Hermitian is just a general mathematical property, while a Hamiltonian is more specific to operators in quantum mechanics. Thought that was a little fun thing that I found. But basically, the substance or the postulate 2 states that every physical property, such as like kinetic energy or linear momentum, exists in operator in quantum mechanics. And so an example is kinetic energy, where in quantum mechanics you have a Hamiltonian operator, which I just realized I didn't put in my example, which represents the physical observables for a formula of physical properties. This is going to be a fairly quick presentation. And so an operator is considered Hermitian if it satisfies the A asterisk equals A prime, which is kind of, I didn't understand exactly what the A asterisk meant. But I know that it represents that it has real eigenvalues, which are operators that are their own conjugate, which I think is like linear algebra. So when you have like the brackets and like 2 variables, it should equal 0. And then their observables and their quantum mechanical operations, you have like the example here, which would be momentum, kinetic energy, your position, potential energy, and stuff like that. And that's kind of everything that I understand about the postulate, and that's the entire presentation, I think. It's pretty small. It's really short. I tried finding more, but I just could not for the life of me.
Okay, so any. Oh, okay. There is a question in the chat line
Okay.
from David. Let's bring up so we all stay muted for maybe 20 seconds, and David verbalize his question if you would like to.
So you say that Hamiltonian and Hermitian are basically the same thing. Are all Hermitian operators Hamiltonians, and are all Hamiltonians Hermitian?
No. Okay, that's really tripping with me. So all Hamiltonians are Hermitian, but not all Hermitian operators are Hamiltonians. Hamiltonian operators are specific to quantum mechanics, and specifically only the I think I noted it, but it was just like the I think I had the classifications in the presentation. So like your time evolution, your energy spectrum, those were the only 2 examples that I could find online. While like Hermitian, I believe, is just if you're using it within, it's just like a general class of operators in math, and like a Hamiltonian is just specific to quantum mechanics, dealing with like that dynamic of like time, energy, stuff like that. Does that kind of answer your question? Like it's kind of like Hamiltonian is a very specific thing, while a Hermitian is more broad. So a Hamiltonian is a Hermitian, but not all Hermitians are Hamiltonians. Like that, hopefully.
Are you satisfied, or you want to add another comment or question?
So I feel like I don't have anywhere good to put it.
Is it okay? Is it acceptable? Okay. Which observable is represented by Hamiltonian?
Observables?
Observable. single one, the only one, is represented by Hamiltonian operator?
I don't know.
Ask help of the class. Or what are units of Hamiltonian?
Oh, it's why can I not for the life of me remember this?
You should know.
It's time? No, it's not gonna be time. Energy. Yeah, actually, no, yeah, energy. That, yeah.
Very good. Okay, let's thanks Sam for participating. So the next presenter is the bravest presenter. We agreed to present two instead of one. Yeah, she was voluntold.
What?
No, it's, I don't know.
Oh.
So on the bottom, good PowerPoint, you see downward.
Ah.
What should number 34? Which way? It's real.
Yeah, so I'm going to be presenting on postulates 3 and 4 today for all my chemists and physicists out there. So let's start with 3, shall we? Because that's first numerically. So my slides are a little bit more information dense. I just put all the information on my postulate on one slide. So I'll kind of break it down for you all. Oh, you can't even read my top part. Is that better?
I think you have to exit out of the transcript.
Oh. Okay, so the sort of formal definition of this postulate is the only possible result which can be obtained when a measurement is made is an observable whose operator is A, is an eigenvalue of A. So first of all, an observable in quantum mechanics includes, but is not limited to, like velocity and energy, momentum, spin, that sort of thing. The equation that I have with the blue, the red, and the green, hopefully we can all distinguish those colors. If you're colorblind, I'm sorry about that. But the blue, the A with the little A hat or bar above it is the operator. And so the operator tells us sort of what mathematical function to perform. Sam was kind of just talking about that. The red, so the wave functions or the eigenfunctions, that's the psi, that's again colored in red. And then the green is the constant or the eigenvalue. So in the equation we see we have the operator, and then our wave function is equal to an eigenvalue of the eigenfunction times the eigenfunction itself, assuming that the constant or the eigenvalue is a real number. So then I have sort of a little example. So if psi is equal to e to the power of a times x, which is an example that we've looked at in class before, if the operator is to take the derivative with respect to x of that wave function, it's equal to a, which becomes the constant or the eigenvalue, times the eigenfunction itself. So basically what this is saying is if an eigenfunction or plural eigenfunctions is the wave function, we can only measure the eigenvalues of that given function. And that's what I have for postulate 3. Do you want me to go on to 4 or just wait?
Please do. Please go.
Okay, so now we're gonna slightly change topics and go to postulate 4. Oh. So postulate 4 is about expectation values, and my name is still Ava. So sort of a similar layout. I have the long, kind of lengthy definition at the top, which is if you let A or alpha be an observable whose operator A has a set eigenfunction, with the corresponding eigenvalues, if a large number of measurements are made on a system, then the expectation value of A for that state, and the expectation value is just the mean of the eigenvalues obtained. It's given by the equation below. So again, I have my little color key corresponding to the integral equation that you see on the right. And I'll go through that equation, but on the bottom left, I have kind of explained in more understandable words what I'm talking about. So if a measurement can be made, so assuming that postulate 3 is good, so that was talking about if you can make the measurement. So assuming that you can, and your wave function is normalized, then we can find the expectation value or the mean if the wave function is an eigenfunction of the operator, then that average is the value of the eigenvalue. So that's still kind of a lot of words. But so the part where I have the assuming the capital A psi is equal to the lowercase a psi, that's sort of flashing back with the last postulate that I had. So assuming that postulate 3 is good to go. If the wave function is the eigenfunction, oh, that's distracting me. So the little purple A with the brackets around it, that represents the average value. So if we take the average value, or I guess to find the average value, you take the integral of psi star times the operator and psi, so psi without the star. So you have both complex conjugates there. So the capital blue, or the capital A in blue, as we discovered with postulate 3, that is going to be equal to the eigenvalue of that eigenfunction. So that's going to be a constant. So you can pull that out of the integral. And so then you're left with psi star, the integral of psi star times psi. And if this is normalized, which we're assuming it is, the integral of psi star times psi is going to be 1. So then we're left with the constant times 1, which of course is the constant. So this is saying that the average value then is going to be equal to the constant that we get out from that given operator, which is where if the wave function is an eigenfunction of the operator, the average value is the eigenvalue itself. And that's all.
So, questions in the audience?
I have one question.
Oh, please.
Oh, yay.
So this tau is a spatial element or momentum element? Because when we calculate the psi, the wave function, we have a k mixture, right? Actually, I'm not asking you, I'm asking the.
Okay. I was,
What is the letter tau in the first equation?
it's, well, the d tau is it's related to the volume.
Okay. I should say.
So that means it's more spatial then?
Yeah. Typically tau is used for time. But
Yeah.
it's a freedom of the author to use any letter. Any questions online?
Oh, that's your question? What is your
Steven,
question?
If you want to ask questions, please go ahead.
Otherwise, if you don't have one, don't worry about it.
Okay, so then let's go to my question. Interestingly, that in both of your postulates, you got the same answer. Result of measurement is eigenvalue. And you did absolutely correct disclaimer for postulate 4 that if the system is in the eigenstate. But what if the result of the this expectation value procedure if the system is not in the eigenstate, or if you measure like ensemble of one example system being one eigenstate, another representative, another eigenstate, like. Can you just write with common?
Well, I mean, I suppose since we're finding the average, if it's not from the eigenstate, the values that we'd be measuring would not necessarily be the same.
Mhm. Yes,
Um,
correct, and average is a very right answer. Like,
yeah,
If there is a 50% to get either one eigenstate or another one, it will be
the average of
mean
the
between
two.
them. Yes,
Yeah,
that's great.
okay, thanks.
More questions to Ava? Questions, so let's thank her once again. And in the remaining 14 minutes, we have 2 more talks. So,
How do I-
postulate number 5 by Elsa.
I don't know how to get,
Eight.
yeah, but that's like not working. Oh, haha. Here, Elsa. Don't say that. Don't say that.
Yes.
Oh.
Melody took my part.
Okay. Mhm.
I love that we're just constantly moving.
Was it G one of your? Yeah, it was.
It wasn't mine, but.
You loved it.
5 to 8 p.m. J10 lab.
Yeah.
Memories were made. in my head.
Okay, what to Elsa?
Great. So I have the effects, postulate 5, the effects of measurements on the quantum state. So measurements as just a broad description is testing and manipulating physical systems to provide a numerical result. But these only provide probable results. Additional information from the measurements is processed that confines the probabilities of an immediate second measurement of the same observable, and then this is able to give you an actual answer. So it's like the more measurements you have, the closer you become to the actual answer. And then the second measurement will be the same as the first, given that it's recorded immediately after the first one. And then the state vector has to change and collapse onto the eigen subspace. So it changes as a result of the measurements. And then the subspace is associated with the eigenvalue that was measured. If the measurement of A on the system in the state of psi, the ket value of psi produces a result of A sub n, then the state of the system is a normalized projection of the ket value of psi onto the eigen subspace of A sub n, shown by this equation. And then if A sub n has a degenerative orthogonal eigenvectors, has degenerative orthogonal eigenvectors, as shown by the equation, the projection operator of the eigenspace will be the function of P sub n. These are this rule has also been stated as the state update rule and the collapse rule. And this rule, along with the Born rule, they form a complete representation of measurements. And so this is where I kind of deviated from postulate 5 based on what I was finding online. So this is based on the time-dependent Schrödinger equation versus the time-independent Schrödinger equation. The time-dependent provides a description of a system that evolves over a period of time as given by the first equation, and the time-dependent Schrödinger equation predicts that a system can form standing waves or stationary waves. In the time-independent equation, it's the Hamiltonian specifically
that's not dependent on time, even though the overall function is. And then I sort of have an example, how the Schrödinger equation can be applied to a hydrogen atom. Q is electron charge, R is the position of an electron relative to the nucleus, R equal to the absolute value of R is the magnitude of relative position. E sub naught is the permittivity of free space, and mu is equal to m sub q times m sub p divided by mq plus mp. The entire equation is given below. And then the equation can be solved by separating the variables. Spherical polar coordinates are the most convenient in this application. So m sub p is the mass of the proton, and m sub q is the mass of the electron, or electron of mass m sub q. The reduced mass in place of the electron mass is used since the electron and proton orbit each other about a common center of mass, creating a two-body problem to solve, which is applicable to like multivariable functions and can be applied to partial differential equations. Motion of the electron is the main interest. The one body problem is the motion of the electrons still using the reduced mass. So it would be just the motion of the electron, not the motion of the electron and proton orbiting each other. And then that's all.
Oh, okay, but. So what was the ball covering the couple, another couple?
Yeah, sorry, Fred.
That's okay. So, any questions?
In the peanut gallery.
Solid.
This peanut gallery has
Any
Thank you,
questions
peanut gallery.
online?
There is a question
A
on.
month, June,
Well, if you want a story about Schrödinger's cat, it's not about Schrödinger's cat specifically, but I used to own a T-shirt that says Schrödinger's cat is dead and Schrödinger's cat is alive.
Okay, how does it relate to question number 5? Got this.
Sort of. So
Just try to make any connection. And it is the most challenging question in the whole course. Not only this.
And so the only thing I know about it is that it has something to do with, because we are not able to observe the cat, it exists both in a state of being alive and being dead at the same time.
Yes.
But as soon as it's able to be observed, obviously we have the answer to that question now.
Can you put a couple of slides better?
I certainly can.
Yeah, enough.
This one?
Yeah. Or if you want, you can, yeah, this is.
This is good.
Mhm.
Do I have any notes? I don't have any notes on this slide.
So let me continue.
Okay, please do.
What Elsa taught us was really impressive and hard to understand that measurement changes quantum system. And if the quantum system is like superposition between alive and dead, yeah, it is in the air until the measurement is done. And measurement either revives him or kills him. And it is done by this projection operator.
Huh.
It is basically what you're told.
Yeah.
Yep.
Of
More
course.
questions, Elsa? Questions 1, questions 2, questions 3. Let's talk about it.
Yeah.
So, last but not least, all right. No, 6 minutes.
Yeah, oh, that's more than enough time. I did mine in 5.
Probably not.
Yeah, come on, Fred, I did mine in 5. You can't
Yeah,
get it.
quite all the answers here.
Well, I could have looked, then I could have given you questions I knew you knew the answer to.
What is the definition of?
I suppose we could have actually been out of. Oh, sick graphic.
Where's the button?
Um,
Right.
Go back to
Oh.
mine. It looks like an old timey desk. Or like a mailbox. Yeah.
This one,
Yep.
tiny desk.
Try to wait for that.
No. All right. My presentation is on postulate 6 of quantum mechanics, and my name is Frederick. You can call me Fred. Here's my super awesome postulate. It says the time variation of the state function of a system is given by that equation, where H is the operator formed from the classical Hamiltonian of the system. Now that's a lot.
According to some, which is energy.
Yes, I'll get to that. Because most of my content has already been talked about today, conveniently. So no, it's okay. It makes it easier for me because that means, like, you know, not all this is wrong. So here's some differences, you know, between the time independent and time dependent Schrödinger's equation. So the one in this postulate is the time dependent equation, which makes sense because it says, you know, it describes the time variation of a state function of a system. Like the state function of a system would be a path independent function like energy or pressure or volume, where you can just measure that in that instance and it doesn't depend on another variable. Like with work exerted on a system, as far as I would understand, like that's not a state function because you have to consider the distance that it travels and anything and everything regardless. The time independent equation just tells you the state of that system, you know, in a specific moment. Like you can find its energy with this equation, but you can't describe like how it changes with time, as far as I understand it, because I kind of don't. And then the time dependent equation is obviously influenced by time rather than location or like the variable x in the upper equation. And it does tell you how something will change with time. So how are these even both Schrödinger's equation? Well, here's, you know, the two different ones in both corners. As it turns out, the Hamiltonian operator can be written like this, which is conveniently the exact same thing as up here, only with a psi in it, just like there's a psi added onto that side. So all of this here, this is the kinetic energy, and that's the potential energy is V. You can just rewrite that as H, slap the psi back onto it, and now you have, you know, they're the same. Wow, like we, you know, here's a simplified answer, you know. So then the E in the original Schrödinger's equation, the time independent one, is equal to H. You'll just have to take my word for it. But in the books, I've also found that E can be written as this, which is crazily the same thing, kind of rewritten as our time dependent equation. If you switch H out for E, since E is equal to H, then, and you know, you move the derivative around and, you know, you isolate it onto that side, we get our time dependent equation. So boom, Schrödinger's time dependent equation. And now all of this crazy math, I have to admit I did not come up with myself, believe it or not. But as far as I understand, you can derive this all the way to get t, time, as like a variable, by moving the time derivative over, taking the integral of both sides, and then you exponentiate that. The e and this natural log on the left side cancels out. So you are left with psi equals e to the c, which will just be a constant. That doesn't matter. So we can just get rid of it. And then, you know, we're left by this e to basically just an imaginary times a constant times time. Time is our only variable that affects this, because, I mean, well, 1 is just a constant, right? I is an imaginary number. H hat is a constant. It's just Planck's number over 2 pi, I'm pretty sure. And then H, our Hamiltonian, is just the energy of the system. And that describes the energy of the system in that. Never mind, I'm getting too far ahead of myself. I don't know what I'm talking about. My point is there's a T here at the end. So the T, this whole equation describes how psi, our waveform in the Schrödinger's equation, varies, you know, with time. Yeah, that's what that's proving. And then I see that we're out of time, you know, we're past class time. So if you want me to continue with, okay, all right. So the time evolution operator, it's just an operator, something you do to, you know, basically just describe how a system changes from one time to another time. And it's written like that. I've highlighted it up there. That's the time evolution operator. And gosh, without, I got to kind of relook at it.
Just summarize.
Yeah. So you can apply it to the Schrödinger's equation via this math that I have written up there. I did it 2 nights ago, so I feel like I should have studied and like re-looked over how I put all this together. Well, here's my, that was the end. Here's my references. I watched a lot of YouTube.
So, Fred did show an interesting logic. In the class, we were going from evolution operator to Schrödinger equation. He showed the path from Schrödinger equation to evolution operator. One can offer several questions, but we do not have time for it. So please email questions to me, and I will.
Oh, yeah.
Ask
I'm gonna get some good ones.
Monday, right?
Yeah, sounds good.
Okay, let's thank all presenters one last again. Everyone gets successful A on the first midterm as a progress towards your final grade. No homework, just relax and come fresh on Monday.
Okay, will do.
Meeting is done. Many thanks for visitors in class and online. And I hope you did enjoy it.